Swayam Prabha. Digital India. Educated India.
So, we will continue looking at solving Ax equals b today, and if you look at this problem, we said the solution is going to be of the form beta I divided by lambda I u superscript I n, okay, where the beta i's are the coefficients of b. We are expressing everything in terms of the eigenvectors. So, this is the eigenvectors of A, this is the eigenvalues of A, and this is the coefficients of B in the ui basis. I am writing B as sigma beta I ui, okay. Now, you see that this particular thing is not going to work when one of the lambdas is 0, okay. If for some I lambda I equals 0, the solution does not exist, okay, and because you are dividing by 0 and you have a problem when you divide by 0, right. So, what exactly does this mean? So, if you have an equation of the form Ax equals b, when does the solution not exist? When A inverse does not exist, because normally you can write x as A inverse b, A inverse does not exist, that is what it means. And if A inverse does not exist, the meaning is that the determinant is 0, because A inverse has the determinant of A at the bottom, okay. This implies the determinant of A equals 0, and remember the determinant of A is the product of the eigenvalues. So, one of the eigenvalues is 0, okay. So, basically all of this is consistent what you have seen earlier in terms of A inverse not existing, in terms of determinant of A being 0, then you can't have Ax equals b, does not have a solution, okay. And you know, you can therefore and you realize that the determinant is nothing but the product of eigenvalues. If determinant is 0, that means one of the eigenvalues is 0, and that is the same thing that is happening here. So, I am just trying to make the connection with what you have already seen, okay. So, now what exactly is the meaning of this thing, and so let us go ahead. I want to talk about what is called the Fredholm alternative or the solvability condition. Okay. Now, that is, if the determinant, if, okay, let us look at this problem. AU equals lambda u. If lambda equal to 0 is possible, if lambda equal to 0 is possible, I have AU equal to 0 has a non-zero solution, because lambda is an eigenvalue, okay, and I put 0, I get 0 on the right hand side, and u is the corresponding eigenvector. The solution that I get, the non-zero solution, is the eigenvector corresponding to lambda equal to 0, okay. This solution is the eigenvector corresponding to lambda equal to 0, okay. So, AU equal to 0 has a non-zero solution. If I say AU equal to 0, of course, it always has 0 as a solution. A 0 is 0, A operating on 0 0, but is there a non-zero u where AU gives you 0? That means lambda equal to 0 is a solution, is an eigenvalue, okay, and the non-zero solution is your eigenvector. So, now similarly, look at A transpose V, A transpose V equal to 0 will also have a non-zero solution, because eigenvalue of A and eigenvalue of A transpose are equal. If 0 is an eigenvalue of A, 0 is also an eigenvalue of A transpose, okay, and the corresponding eigenvector is V. V is the eigenvector corresponding to lambda equal to 0 for A transpose, okay. So, the question I am going to ask here is, I have Ax equals B and A transpose V equal to 0, okay, and we are looking at this condition here. So, basically one of the eigenvalues is 0, okay. When does this equation Ax equals B have a solution? What is the condition for Ax equal to B to have a solution? So, what I am going to do is I am going to take the inner product of this with V and inner product of this with X and subtract, okay. So, I am going to do inner product of V with Ax equals inner product of V with B, and I want to here, I want to A transpose V with X equals inner product of 0 with X. So, I am just doing inner product of the first equation with V, inner product of second equation with X. Now, this inner product of V with Ax is A transpose V X, inner product of A transpose V with X, okay, and if I subtract, this will go to 0, okay, subtract against 0 equals inner product of V with B. So, the point I am trying to make here is that in order for a solution to exist, the B has to be perpendicular to V, which is the eigenvector corresponding to A transpose for lambda equal to 0. Only if B is orthogonal to V, I will have a solution. Okay. So, this condition, this is called the solvability condition. Okay. Now, let us take an example to understand what this means. Take 1, 2, 6, yeah, this is my A, X equals B, okay. This is my A matrix now. I want, you can see that this particular row is dependent on this, 3 times of this row gives me this row, or 2 times of this column gives me this column. So, there is a dependency, okay, and that is basically what is causing this lambda equal to 0, okay. So, basically the rows and columns are dependent. This implies lambda equal to 0. I am just illustrating for a 2 by 2 case, but if you have 3, same thing, one of the rows and columns are independent or dependent, sorry. So, let us find the eigenvalues of this. The determinant of this must be equal to 0. This implies okay. So, I am not going to worry about this other eigenvalue now, my focus is on this eigenvalue only, lambda equal to 0 eigenvalue, because I want to find the eigenvector corresponding to lambda equal to 0 for A transpose, okay. So, corresponding to A transpose, so lambda equal to 0 comma 7 also for A transpose, because eigenvalues of A and A transpose are the same, okay. And what is the eigenvector for A transpose? A transpose turns out to be 1 3 2 6, this is A transpose, okay. And corresponding to lambda is equal to 0, for lambda equal to 0, the eigenvector is, I will subtract 0 from this, right. We solve A minus lambda I x equal to 0, okay. The solution x corresponding to lambda equal to 0, basically I will solve for A x equal to 0, sorry, A transpose. Now, I am looking at the transpose now, 0, which means 1 3 2 6, so u1 u2, what I put x, no, then let me call it x1 x2. I have x1 plus 3x2 equal to 0, 2x1 plus 6x2 equal to 0, okay. So, now how do you find the eigenvector, because they are, I don't, if I have 2 independent equations I will get only 0 as the solution, but these 2 equations are identical. So, I need to work with only one of them, and I can just set x2 equal to 1 and x1 equal to minus 3. Okay. So, the corresponding eigenvector is minus 3 1. Okay. This is the eigenvector for A transpose corresponding to lambda equal to 0. Okay. This is eigenvector for A transpose for lambda equal to 0. Now, what does the solvability condition tell me? That this B has to be perpendicular to this V for a solution to exist. Okay. From the solvability condition, inner product of V with B must be 0. Okay. And let us say B is B1, B2. So, basically I am saying inner product of V is minus 3, 1, B1, B2 or B2 minus 3 B1 plus B2 must be 0 or B2 must be 3 times B1. Okay. This is what the solvability condition tells me. It means this vector has to have the form, if the first element is alpha, the third element has to be 3 alpha, second element has to be 3 alpha. Okay. Whatever is the first coordinate, second coordinate has to be 3 times that. Now, that makes sense because this left hand side, this is 3 times that. Okay, only then I can get a solution, I will get an infinity of solutions. So, point is, this is what you have seen as equation being consistent. These two equations are now consistent. X1 plus 2x2 gives you alpha, 3x1 plus 6x2 gives you 3 alpha. The two equations are consistent. This is what the language you have seen earlier. You have a system of consistent equations. Okay. So, basically, solvability condition ensures the equations are consistent. Okay. And if B is anything is not equal to this form alpha by 3 alpha, equations are inconsistent and no solutions exist. Okay. Now, you can see that with 1, 4, 2, 3, whatever it is, then those two equations cannot be satisfied simultaneously. Okay. And if it is consistent, you will have an infinity of solutions. So, basically, if B is not equal to, if inner product of V comma B is not equal to 0, then what? No solutions. And I want to emphasize again, V is the eigenvector for A transpose corresponding to lambda equal to 0. Okay. If it turns out that, so all this is only when lambda is 0. If lambda is not 0, there is no problem, because then A transpose V equal to 0 will have only 0 solution. Okay. If lambda is not equal to 0, then A transpose V equal to 0 has only 0 as a solution. So, then of course, inner product of 0 with any B will be 0. Okay. Then the solvability condition is automatically satisfied, because V is 0, so inner product of V with B always. Now, we want to go and, so that is basically trying to talk about solvability of a system of equations, not in terms of rank. Earlier, I think in your earlier course on matrices, you have talked about matrix of A, rank of AB and all that. We are not talking about rank here. Okay. I mean, I sometimes use the word rank just to make the relationship with what you have seen earlier for clarity, but we are sticking to the operator, eigenvector, eigenvalue, and trying to make these connections. Okay. But all of these are kind of related to each other. So, this is your solvability condition, and if this condition is satisfied, equal to 0 is satisfied, then you have solution, otherwise no solution. Solvability condition ensures consistency of equations. Okay. Now, I am going to basically work out the problem where Ax equals B. Yesterday we did the problem where A was equal to A transpose. Okay. So, we did not have to really worry about what are the eigenvalues and eigenvectors for A transpose, but now I am going to look at a problem where A is not equal to A transpose. Okay. And to keep my life simple, we will do as it is 2 by 2. A x something like this. Yeah. So, that is the equation I am trying to solve. Okay. This is Ax equals B. So, what I have to do is find the eigenvalues and eigenvectors for A, and now the eigenvectors of A are not going to be orthogonal, but I need to therefore find the eigenvectors of A transpose also, and then use this bi-orthogonality condition. Okay. Because there is a relationship between A and A transpose eigenvectors, that is the idea. So, because it is not symmetric, I have to find the eigenvalues, and eigenvalues are the same, eigenvectors for both A and A transpose. If it is symmetric, eigenvectors of A and A transpose are the same. Okay. So, let us do that, find the eigenvalues and the eigenvectors, and let us do for A first. So, I have the lambdas satisfy 1 minus lambda 2 8 1 minus lambda equal to 0, which is 1 minus lambda squared minus 16 equal to 0. So, lambda is 1 plus or minus 4, which is 5 and minus 3. Is that right? So, I have two eigenvalues now, 5 and minus 3. The first thing is you heave a sigh of relief, there is no 0. So, you do not have to worry about solvability condition, this definitely has a solution, right. If lambda equal to 0, then you have to look at what I did earlier. So, now so let us call lambda 1 5 and lambda 2 as minus 3. You will call something number 1. Corresponding to lambda 1 1, I want to find the eigenvalues. Eigenvalues are done, eigenvectors. Okay. So, what is u1? u1 will be solution of a minus lambda I x equal to 0, which is a will be this lambda is 5, right. So, I am subtracting 5, minus 4 2, 8 and minus 4 x1 x2 equal to 0, the solution to this. Okay. So, basically I am putting lambda as 5 and I got minus 4. So, basically this is minus 4 x1 plus 2 x2, 8 x1 minus 4 x2 equal to 0. They are basically dependent equations. Okay, minus 2 times this gives you this. So, I am going to put x1 equal to 1 and I will find x2 equal to 2. Okay. So, the first eigenvector u1 is 1 2. U is for A. So, eigenvector corresponding to lambda equal to 5 is 1 2. Okay. Clear? Now, what about u2? u2 is the solution of A minus lambda is minus 3 plus 3i x equal to 0. Okay. Now, let us add 3 to the diagonal, 3 plus 1 4 x1 4 2 and 8 4 okay. So, I have just added 3 to the diagonal. What do I get? I get 4 x1 plus 2 x2 equal to 0 and 8 x1 plus 4 x2 equal to 0. So, now if I put x1 equal to 1, I get x2 equal to, what do I get? 1, I get minus 2. Okay. That is my solution. This is my u2. Correct, no? Yeah. I thought they became orthogonal. I was a bit worried. Now, what about the inner product of u1 and u2? What about the inner product of u1 and u2? It is 1 1 minus 4, so minus 3. This is not equal to 0. So, basically the eigenvectors are not orthogonal. Okay. So, if you remember last time when I found the solution, I just said take the inner product with the eigenvector. I can't do that because if I did that, again I have a system of 2 equations in 2 unknowns for finding the beta or Ci. So, that is a useless method, right. So, but I will now find the eigenvectors of A transpose, okay, corresponding to the same eigenvalues. So, let me summarize this somewhere. Lambda 1 is 5, lambda 2 is minus 3, u1 is 1 2 and u2 is 1 minus 2. Okay. So, now I need to find the eigenvectors of A transpose. So, now determinant of, so to find the eigenvectors of A transpose, I have determinant of not determinant, I have to solve A transpose minus 5i x equals 0 and A transpose plus 3I x equal to 0. Okay. I have to solve A minus lambda I x equal to 0. So, this is what it is. So, A transpose is, let me write it here, this is 1 8 8, this is minus 4 and 8 will come here and 2 will come here. I am subtracting this, so I am getting minus 4. Just make sure I am not making a mistake. I have subtracted 5, yeah. And for this one, I add 3 to the diagonal, I have 4, 8, 2 and 4. Okay. So, you have to solve these equations. You get minus 4x1 plus 8x2 equals 0. Here I have 2x1 minus 4x2 equal to 0. So, basically if I were to put x2 equal to 1, I get x1 equal to 2. Okay. So, I get, so the, which was the first eigenvalue? 5, no? So, this is V1. V1 will be 2 1. I put x2 equal to 1. See, so whenever you are solving the eigenvectors, okay, there has to be a dependency in the equations. So, you see this dependency in the equations, you are getting the same equation. If you have 3 equations, one of them will be dependent on the other 2 or 2 will be dependent on one of them, whatever, there will be a dependency, only then I can get a non-zero solution. Okay. So, basically V1 is the eigenvector corresponding to lambda 1, 5, okay, that is 2 1. And what about V2? V2 will be so you get V2, the solution will be x2 equal to 1 minus 2 1. Okay. So, I need to calculate the eigenvectors of A transpose because the matrix is not symmetric. If the matrix is symmetric, eigenvectors of A and A transpose are the same. Okay. So, basically what I have done, I first calculated the eigenvalues, then I calculated the eigenvectors of A, then I calculated the eigenvectors of A transpose. And you have to be careful about the numbering. The first one eigenvalue u1, second one is this. So, now V1 is 2 1 and V2 will be minus 2 1. Okay. So, basically that biorthogonality property that I spoke about earlier, I am illustrating that with an example. Minus 2 1 is orthogonal to 1 minus 2. Minus 2 1 is orthogonal to 1 2. Okay. Inner product of u1 with v2 is 0, inner product of u2 with v1 is 0. That is the biorthogonality. I mean, if you have an n dimensional matrix, you will have everything else will be u1 with v1 is not 0. Okay. If only if the i's are different is 0. Okay. I mean, you would actually do a complex conjugate. If you remember the thing, you have to do complex conjugate, but since we have only real, we do not worry about it. Okay. So, we should do this actually. We do not worry about complex conjugate because everything is real. So, now if I want to solve this equation, Ax equals B, I need to write B as in terms of the eigenvectors of A. Okay. I will write B as sigma beta I ui, which is beta 1 u1 plus beta 2 u2. Okay. Again, whatever I did last time, I am doing the same thing. Only thing is the calculation of beta I will do in a slightly different way. Last time I took inner product with ui, u1, then this became inner product u2 with u1 was 0. Okay. Now, because inner product of u2 with v1 is 0, I will take the inner product of this with v1. You understand? I am going to take the inner product of this with v1 to get now the orthogonality is with the other fellow. So, this guy becomes 0 now, and I can calculate beta 1. Okay. So, what is beta 1? Inner product of V1 with B is 4 and 17. 4 2 is 8 plus 17, 25 divided by V1 with U1. Two and 2, 4. Is this right? That is beta 1 for you. And what about beta 2? Will be similarly beta 2 will be inner product of V2 with B divided by inner product of V2 with U2. Okay. I will take the inner product of this equation with V2 now. Okay. And then you will see that this will cancel, this will contribute. Where is V2? V2 with B minus 2 minus 8 plus 17, how much is that? 9 divided by V2 with U2 minus 2 minus 2 minus 4. So, this is how I find beta 2. So, basically you have to take the inner product with the V, not with the U. Okay. Any questions? You can verify what I have just done. B was 417, right? This is 417, and what did I find beta 1? 25 by 4. What is U1? 1 2, and this is minus 9 by 4. U2 is 1 minus 2. So, 25 minus 9 is 16, right? Why am I getting 4, man? I made a mistake? Oh, I am supposed to get 4. Yeah, I thought I was supposed to get 1. This gives me 4, and 4 2 is 8. Oh, sorry, 25 times 2 is 50 plus 8, 58 divided by 4, that is 17. Oh, thank God. Okay. So, basically I am just trying to show you that the beta 1 and the beta 2 that we found are correct. Okay. And rather than solve a system of equations to find beta 1 and beta 2, I just did inner products to find the beta 1 beta 2, exploiting the orthogonality with V1 V2. Okay. So, we exploited the orthogonality and we were just do one inner product, get the coefficient, and I am just verifying that the coefficients that I found out are indeed correct, because B was represented in terms of this is my basis now. I am choosing the eigenvectors of A as my basis, these are the coefficients which I found and this is what I get. Okay. So, now basically we have represented this B in terms of the eigenbasis and these are the coefficients. Okay. Now, what about x? Who cares about beta? We want x, right? We care about x, that is what we have to find out. So, x will be the same thing what we got earlier, sigma beta I by lambda I ui equals 1 through 2. Okay. And beta I just found out, what is it? Beta 1 is minus 25 by 4 and what is lambda 1? 5. So, 25 by 4 by 5, that is 5 by 4. So, I get 25 by 4 by 5 and u1 is 1 2 plus this is x. Okay. Beta 2 is minus 9 by 4 and lambda 2 is minus 3, minus 9 by 4 by minus 3. So, let me put it as plus 9 by 4 and 3. And what is u2? 1 and minus 2. Okay, that is my x. So, that simplifies to what? This 5 by 4. So, I have 3 here and I have 5 here. So, 5 plus 3 is 8 divided by 4 is 2 and I have 5 to 10, right, minus 6 and clearly this has to satisfy, right, 2x1 plus 2 times this plus this gives you 4, 2 times this plus this gives you 17. So, that is your x. I mean, this may look like a very complicated way of doing things, but when you have to deal with large number of equations like I told you earlier, this is straightforward because you just do not have to do any iterative scheme like Gauss-Seidel, Gauss-Jordan, you keep guessing and all that. You just get the thing in one shot, okay, and the number of operations you have to do to get the solution is easy, straightforward. So, basically what I am saying is this is what you have to do when you have a general matrix which is not self-adjoint. When A is not equal to A transpose, you exploit the bi-orthogonality property of the eigenvectors between A and A transpose, because eigenvectors of A are not orthogonal. Eigenvectors of A are orthogonal to the eigenvectors of A transpose, something like that, okay, and that is what you have to use. So, all that theory that we did is basically applied for solving problems of this kind. You have to sit down and solve problems and convince yourself. I have done the 2 by 2 case. If you have a 3 by 3 problem, you extend it, you will be able to get it. I think the theory is that I can discuss the theory for the general problem tomorrow, and then we will start solving some ODEs, ordinary differential equations tomorrow. Same whatever approach we have used so far, we will use it for ODEs.